All right, Chapter 1, a grand tour of the heavens. And this is going to be Section 1-2. How do we study things that we can't touch? You're probably taking this course in astronomy because maybe you've seen Carl Sagan's Cosmos, or you've seen some other documentaries, or you've seen photos from the Hubble Space Telescope, or some kind of great science fiction series, or something that's maybe inspired you with awe, looking at these beautiful, beautiful images of things out in the universe, the planet Jupiter, or the rings of Saturn, or a nebula, or a supernova remnant, or something like that, or another galaxy. There's wonderful things out there. But these things that we study in the universe, these things that we want to learn about, black holes, galaxies, nova, pulsars, all these things, we can't actually touch them. You can't take a sample of a black hole or a pulsar and bring it into your lab and weigh it, or measure its mass directly. You can't do that. They're too far away. All right. You just can't do that. So how can we study these things if we can't actually touch them? Most scientists, biologists, they've got these animals, they've got these cells that they can study. Zoologists can go out and get this animal. Geologists can go out and get a rock and learn about that rock. But how can we do this in astronomy? How do we learn about things? Well, we use the only thing that the universe gives us, and what the universe gives us is light. We study the light that we get from an object, and that's how we know about it. And really, what you're going to learn, hopefully through this course, is that astronomers do fantastic things just by studying the light that an object emits. Now, early astronomers like Galileo or Newton, they studied the visible light just by putting their eye to a telescope, and they made drawings of what they saw. And that's a wonderful way to study things. But that's the beginning, right? What more can you do? Well, scientists discovered that they can take that light that's coming, that visible light that you see with your eye, they can put it through a spectrum, through a prism, and they can make a spectrum of that light. And by looking at that spectrum, they can find out something about that object that emitted that light. Okay, so this is an example of a spectrum. All right, it looks kind of like a rainbow, and you can see that. Okay, you can see this rainbow pattern here, but look at this. You've got parts that are missing. There's colors that aren't there. Right? Some of them are kind of faint, but there's some of them really dark, obvious missing things. What's going on? What is that? Right? Well, astronomers will see that, and they'll figure out what's going on with that object based solely on what's not visible. They can tell what something's made out of just by studying its spectrum. We can look at the spectrum of the sun, and we can tell the chemical elements that are found in it by studying the sun's spectrum. So even without having a sample of the sun, we can tell very, very exactly what the sun's made out of. All right, but it's not just the spectrum, not just the visible light we can work with. There's a whole range of electromagnetic radiation that we can look at. Visible light makes up only a very tiny part of the electromagnetic spectrum. You've got this huge array, this huge, vast electromagnetic spectrum that you can study, of which visible light is only a tiny part. We can study radio waves, the same type of stuff that you pick up with your car radio, right? We can study that with telescopes built on the ground. We can study radio waves, and we can learn about distant objects in space from that. Okay, we can use obviously telescopes like we use, like we're going to use in this program. Or these larger professional telescopes, to look at visible light from the ground or from space. The Hubble Space Telescope, it looks at visible light up in space. Or if we get up above the Earth's atmosphere, which, as we're going to learn in later chapters, the Earth's atmosphere keeps a lot of this electromagnetic radiation from getting down to the surface where we could study it. We get up above the Earth's atmosphere, and we can study things like infrared radiation, which a lot of times you would perceive as heat. All right, or we can study ultraviolet radiation from some objects that have a little more energy. This ultraviolet radiation is the same thing that gives you sunburn or tan skin. We can study X-ray radiation being emitted from even more high power or hotter objects. X-rays, the same stuff that your doctor uses to X-ray a bone, or your dentist to X-ray your teeth. And even from very, very hot, very energetic objects, we can measure gamma ray radiation. Gamma rays, which, from comic books, it turns you to green, hulking, muscular monsters. Or it's just very high energy radiation which can go through you. All right? Hey, it's the Incredible Hulk. But, we can study all of this from astronomy, from objects that are emitting it. And we can learn about these objects just from studying that light. All right? So we've got a wide array of what we can use, not just visible light. We've got all of the electromagnetic spectrum that we can use. We look at objects in the visible and we take images. Here we have an image of the double cluster in Perseus, and you see these two clusters of stars. It's wonderful, wonderful view. Hopefully we'll get a chance to look at that through the telescope. And you just see this magnificent image, this magnificent field of stars clustered together. And it's beautiful. But we look at it in X-rays, like this image from the Chandra X-ray Observatory. And we can learn a lot more about what's going on just by looking at where all the energy is. All right, what are these X-ray sources? What does this mean? What's going on? What's happening there? We can learn a lot about the universe by looking beyond visible light into the invisible radiation, the X-rays, the gamma rays, the infrared, the radio waves. That tells us a lot more than when we can see just with our eyes. All right, the telescopes that work in the optical, like we've got these giant telescopes here. They have mirrors now that are 10 meters across. 10 meters! That's huge! That's more than 30 feet, okay? That's a huge mirror. And remember, the larger the mirror is, the better resolution you get. It's kind of like having a camera with more megapixels. The more megapixels you have, the clearer and the sharper your image is going to be, the more detail you can see. And with these large telescopes, with these large mirrors, you get incredible detail. And so earthbound telescopes, they're getting large with this. They're getting huge mirrors. But we can take those mirrors, and obviously we can't take them as large as, a 10-meter mirror, but we can take, fairly large mirrors and put them up in space, like with the Hubble Space Telescope. And because we're up above Earth's atmosphere, we're able to see many more beautiful images. We can see detail, like in this image from the Large Magellanic Cloud. We can see detail that we could never see from Earth, at least until recently. Ground-based astronomers are starting to get to a point where they can do some of this work, seeing some of this kind of detail that the Hubble Space Telescope can see. But the Hubble Space Telescope, because it's above the Earth's atmosphere, we get much more detail. And you've all seen beautiful images from the Hubble Space Telescope. We can also, though, look, in space, and again, I mentioned, we can look in the X-ray or other wavelengths, and we get a much more dynamic image of what's going on. This image, these are actually the same thing, okay? What you've got here, this is an image of the Crab Nebula, okay? The Crab Nebula, is one that hopefully we'll get a chance to see in one of our observing sessions. And, you look at it through a telescope, and you're going to see this kind of fuzzy patch, and if you use like maybe the Hubble Invisible, or if you use, a good ground-based telescope with, a good camera attached to it, you can get this kind of, really much more detailed image. You see clouds, and you see other structures in there, and it's beautiful, it's gorgeous, but it's still kind of, it's the visible. It's, it doesn't tell you a whole lot about what's going on there. But let's look at it in X-ray. Here's the same thing in X-ray, and you get this wonderful dynamic image of something's going on. All right, you have this matter that's being swirled around this very tight object at the center, and there's stuff coming off of this. Right? Well, what's going on is the Crab Nebula is a supernova remnant. You had a star that reached the end of its life, and in a cataclysmic explosion, just scattered material all throughout the galaxy. And what's left behind is this tiny little remnant, a neutron star that's spinning very, very fast. And it's got a very high strength magnetic field, and that magnetic field is causing these particles to be shot out along the axis right here. And it's also causing other material to be wrapped around it like this. And that's a pulsar. That's what we call a pulsar. We can see with X-rays, we can see a much more dynamic image of what's going on in the Crab Nebula. So We study things we can't touch basically just by looking at the light. So we're looking at the light from these objects, and that light alone is enough to tell us many wonderful things about the universe around us. So that is section 1-2. How do we study things we can't touch?